back to the last session of this workshop. Yeah, this is really a kind of open-ended thing. I'll be totally honest, it's something I've wanted to look at for a while, never had time, and thought that this was the perfect opportunity to start looking at it. So I rather frequently called it Getting to Know Big Audio Data. It's kind of following on from the stuff I was talking about in the first workshop, where we might have huge databases of sound and we necessarily need to collect more than we can listen to in certain situations. And getting to know I use very broadly here. It might be, and there's different senses, all of which I'm interested in, which is as a sound recordist, you might spend hundreds of hours in a place really getting to know, have a sense of place of a sound. You might be a humanities scholar getting to know some, or history auditor, some sound artist or whatever. And in the situation I'm thinking about soundscape ecology, which is a funny mix in a way of both empirical and speculative listening, we could say. So what I want to do by way of introducing this session is think about why we might want to know big audio data and how some of the existing ways in which we do it. And that will frame then an introduction from Dimo Schwartz, who I think you've all met by now, who's been working on for a number of years on a fantastic system called CatArt. And that'll frame, if you like, the perception challenges that I posted on the blog. So it was by no means mandatory homework, but some example audio data sets, one of which came from some interest from humanities, particularly oral history scholars in our department, of how we might use machine listening in new ways to understand oral history databases. And so we looked at the example of gender dynamics and bias in basically do men interrupt women more in conversation, and it was kind of a trademark of the Trump discussions. And it's also been shown, there's some recent research in the Journal of Social Science showing that they analysed a corpus of interviews in engineering department, job interviews I think it was, and hand annotated videos of that material, and showed that women are interrupted an awful lot more and never often finish their presentation because then they're constantly saying, sorry, I haven't got quite got time. So there's a kind of interesting use there of looking, almost bringing in empirical methods into oral history. And then the other one was a set of environmental recordings to see whether we might be able to perceptualise, let's say, audio features in new ways to have us not to find empirical results, but to help us interpret maybe those empirical results. So why might we want to do this? In some ways it's the opposite of the Gary Barlow example that Chris so fantastically provided. We're interested in how Gary Barlow's dances, we don't really care what the meaning of Gary Barlow's gestures is in reference to the style of music. As long as he dances consistently and we can recognise that, that's fine. We don't really care what's going on inside the network. And in some situations, it really matters how things are working. So in this example, I've been working in this field of soundscape ecology, which is quite new and a little bit speculative in some ways, because compared to music information retrieval styles, which we'll come back onto, where we have, if you like, the ground truth is certain. Here the ground truth is a little bit slippery and speculative. So what we're interested in is, can I find my mouse? There it is. Can we measure this acoustic, what we're interested in is finding a proxy for the ecological community, so for the structure, what distribution of species are there. And what we're assuming is that of all the species that make a sound are a good proxy or a good indicator for the wider community. And that's kind of accepted. Basically, birds are a really good indicator, for example, and frogs in other situations. But of course, the birds and the frogs and the insects and the mammals aren't the only things making sound. Loads of stuff makes sound, wind makes sound, people make sound, cars make sound, planes make sound. So our indices are capturing all of the soundscape, but we only want to be concerned with the ecologically relevant changes in soundscape. So it gets a little bit more complex. We haven't got a straightforward ground truth, we've got sort of some sets of assumptions on top of each other. So I talked in these sorts of terms in the first workshop. And the issue with verifying indices. So here what we're trying to do is we collect a bunch of data, so we record a big audio data set. We have our ground truth, which is the sort of traditional way of monitoring biodiversity, which is to count species, basically log different species distributions. And then we basically calculate a bunch of audio features on those audio files, and we compare them. So we build some statistical model, and then we need to interpret that model. And what I was talking about is necessarily we've got so much data. In order to have a statistically solid model, we need to collect more data than we can listen to. So that makes the interpretation hard. And there's a few other steps. Like the first reason we might want to find some way to perceptualize, even a very simple visualization could be really helpful, is to check the integrity of the data. So first off, you come back from the field, you've got 10 terabytes of data on your hard drive. Were the recorders all on for the whole week you were recording across the 25 sites? Was the batteries on that in some, and the files silent? Was it really windy and the whole thing was clipping the whole time? Was there some like electrical fuck up in it and it distorted? So just a really basic kind of integrity check. And that's true in other domains, right? If you have a huge sound-up database or a huge oral history archive, if you just acquired a whole audio archive as a librarian, you might want to just very quickly and rapidly see what's the kind of state of these files. So that's the kind of simplest use case, if you like. And then we come on to like trying to understand, if you like, and this is why I say it's a little bit opposite from the Gary Barlow example that Chris was saying, because in that situation, as long as it works, we don't really care how it works. So it's solid and it's fine. If it works, it works. In this situation, we're trying to understand something about the world. So we've got this sort of long chain of abstractions, if you like. There's the ecological community in the world. We're assuming there's a relationship between that and the acoustic environment, and then we're making a recording of it, and then we're calculating some features on it, and then we're building a model. In this case, I've been using multivariate random forests, and then we get some model stats out. We've got the R squared and the error rates of that model, and then we need to make some interpret that and see, well, what does that really tell us about all those boxes in the chain before? And yeah, it gets a bit opaque. We can't necessarily interrogate. When we use something like, when we use models like multivariate forests, where we can't even like print out a forest and check it makes sense, right? Because we've got a whole bunch of them and we'd have to look at all 1,000 of them to know we can't do that either. So we need to really understand what those basic stats mean. And that's another issue, another reason I'm saying this sort of getting to know is quite a sort of hazy, like wouldn't it be nice to be able to sort of somehow explore that data set to check that, yeah, it really was ecologically relevant, these things that are showing, hopefully, some strong statistical similarities. So, simply put, there could be some confounding variables, right? We don't know if the things that were making the sounds are the ecological entities of interest or some other aspect of the soundscape. And this has been discussed well in music information retrieval, which we'll come back into in a sec. So, quickly to summarise then, there's a few reasons why we might want to do this. We might want to check the data, integrity of our data, and that's true in any situation. We might want to use it to help us interpret the model, and that's probably only in more empirical situations. And also just scooping around, exploring a big database, we might gain fresh insights in the same way as you do if you're sitting in the field for hours and hours and hours recording something. You have an understanding of that soundscape, which can lead to new insights. So what are the existing ways of doing that? Well, the first one is just that, sitting in the field for thousands of hours. You get to know in a way that you can't know through looking at a bunch of numbers. A kind of deeply experiential, situated way. And if we've had that experience, which you get partially, so if you spend 3 months in the field setting up recorders in different sites and coming back, you do get to know those sites in a way, but you obviously haven't listened to every minute of every recorder in every site. So that's great, that's a kind of an ideal, but we can't do it. So part of this question is like, how can we keep some of the characteristics of that kind of knowing when we've got big data sets? So the other way of doing it is to use analytic methods. So has anyone heard, all of you know Bob Stern? Vaguely, have you heard of his horse project? So he's had a really nice project that he's working on, I think since 2014. Yeah, 2014. So he's thinking about working music information retrieval, and thinking about quite relatively simple tasks, well, not simple at all, but like conceptually simple tasks, so key detection, genre recognition, this kind of thing. And focusing on the issue of these confounding variables, right? So you might get a figure of merit, so your confusion matrix, your precision rates, etc., for key detection, music genre recognition, etc. But how do you really know? So, and maybe they're really high, right? Maybe you're getting like 75, 80% correct. And how do you know if what the model is working on are the features of interest to you as a human, i.e. are they musically relevant? So he uses this lovely analogy of clever hands. Has anyone heard of clever hands? Yeah, so clever hands was a horse owned by Wilhelm von Osten in the 1800s, something like that. And clever hands was amazing. He could do abstract thinking. He could do quite complex arithmetic problems. So he could add, he could multiply, he could factorize even. So he would, what's his name? Wilhelm von Osten would bring him out into the town square and he'd say, clever hands, give me the factors of 28. Clever hands would go. And so on and so forth. And he'd scrape out on the floor the answer to whatever mathematical problem he gave him. So this was pretty amazing, right? And everyone said, oh my God, like maybe humans aren't unique in abstract thinking. Horses can do maths. This is totally amazing. And then Dr. Oscar Fultz came along and said, I'm not so sure about this. I think there's something else going on here. So he designed a set of experiments which basically isolated the confounding variables. So he said, right, is this horse really doing maths, or is there something else going on? So first thing he said, well, most obvious thing is Wilhelm is giving him some clues, right? It's like, he's like wiggling his fingers or he's doing something else. So he said, right, somebody else come and ask Clever Hans a question. Clever Hans got it right. Bloody hell, this is amazing. Okay, so maybe there's something else going on. Is it a visual cue? So he blinkered Clever Hans and he got the person to ask the question, so orally, out of sight. Clever Hans couldn't do it at all. He's like, okay. So there's something visual going on. We can't do it just by sound. But is there something else as well? So then he thought, right, maybe it's to do with a cue that the person is giving Clever Hans. So he got two people, gave them each a number, and asked Clever Hans to give the sum of those two numbers. And those two people didn't know what number the other one was giving, right? So then nobody who asked Clever Hans the question knew the answer to the question. Clever Hans couldn't do it. Right? So what he worked out was that the person who was asking the question was actually leaning in. So when they asked the question, they'd go, factors of 28? And every time he gave one, they'd be like, amazing. Amazing. And what Clever Hans was doing, he was shit at maths, but he was amazing at like intersubjective non-verbal communication and perception, right? So he was sensing when this person had heard the answer that they wanted. So this has become known as like the Clever Hans effect. So that you subconsciously provide the answer to whatever you're system that you're asking a question to, but you're providing it in an irrelevant domain, right? You're giving it, it's working on a feature other than that which you think is of interest. And this happens all the time. Like anyone who's worked with evolutionary computation will know that it's really easy to design a fitness function. If you can design a fitness function and you design a really good set of operators, and if the operator is decent, they'll find a gap in your fitness function and they'll solve it in a way that you didn't mean them to. And this has happened again and again. There were some amazing like evolutionary hardware experiments in Sussex in the 90s where they evolved field programmable gate arrays to make circuits, and they created these solutions with like less gates than any human could ever achieve. But when they looked at them, they were like, what on earth's going on? They're not even connected. Like what is going on? And then they worked out that actually it was using some other component in the room. I can't remember what it was. It was a radio or something. It's like using a radio or television or a toaster or something in the room to solve the problem, basically. And it has the same things in evolution robotics, like evolving navigation problems, and you set it up you think you're asking the robot to like follow a triangle in a circle, but it's finding some other consistency in the environment to solve the problem through. Right? So it's kind of quite a familiar problem in AI, basically, in machine learning systems. So what Bob's done is he's set up this method of irrelevant transformations, and he said, okay, so if I'm concerned about key detection, and I can't tell from these figures of merit from confusion matrices whether my system is like properly analysing all of the chord sequences and saying, yes, it's C minor, or whether it's just looking at the first chord and saying, let's E flat, C somewhere, so yeah, C minor, let's call it C minor. So what he's done is given a kind of analytical solution to say, well, what we'll do, we know what the ground truth is, we know what the system should be basing its answers on. If we transform the data in ways that are irrelevant to the solution, and it still gives us a good solution, then probably it's using that. And vice versa, we can change other things. So in the key detection, if you chop off the first bar, it shouldn't matter to a human, right? You could time stretch it a bit if you maintain pitch. You could play on a different instrument. These are all transformations that don't affect the pitch. If the system gives us an answer, probably it's working on something else. So that's a really nice way of doing it analytically, but in situations like in soundscape ecology, we've got this kind of extra step of woolliness in a way, because we haven't got a solid ground truth, so we can't use, at the moment, there might be situations we can, but using these kind of purely analytical techniques isn't really possible. So to step to the other extreme, we can visualise things. So we can't look at spectrograms are really super. We all learn very quickly to read things with spectrograms, but they only really work on minutes at a time. Like even if you go up to hours, certainly not days, weeks, months, years, which is the sort of timescales on which ecological dynamics of interest might happen. So a guy called Michael Towsey in Australia has come up with these, what he's calling false colour long-term spectrograms. So they're very similar to this slightly woollier one, but you can sort of see a little bit better what's going on. He's rather than, so we've still got time and frequency, and brightness is some kind of magnitude, but instead of compressing, so this is 24 hours. If you compressed a normal spectrogram on that scale, everything would get just blurry and a bit weird. And it doesn't actually say, I wonder whether that might be what the bottom one is, I'm not quite sure. But what he does is basically calculate a bunch of audio features and then pick 3 of them and assign those to RGB values. So those features, in this case, is cover, spectral cover, which is sort of saying get a spectrogram and then just see what percentage of that minute is above a threshold. Acoustic complexity index, which is sort of saying split up chunks of time and frequency bands and then see how much the energy changes over those frequency bands over that time. So it's a sort of measure of sudden change of energy in a sound file. And temporal entropy, which is Shannon's entropy. Shannon applied to a Hilbert transform of the waveform. So it's slightly arbitrary which indices you pick, and the representation will be as good as the indices. But it's quite a nice way of quickly seeing, and he shows that you can see kind of species and recognise key soundscape patterns coming out. So that works quite nicely on a kind of 24-hour range, and he's developed another way of doing that over much longer time scales. So now each pixel is a minute of data, and he's got 12 hours along the x-axis, and then each row is a different day. So there you've got what, six months, March, yeah, something like that. And you can see quite nicely there, so where the dawn chorus is changing, and you've got this time. You get a good snapshot, I suppose, of long-term data. So that's quite a nice way of doing it, but then you can't sort of dive back into it, if you like. So I'm wondering, there's a few different ways of knowing sound data, sound databases. We can listen, but we'd have to listen forever. We haven't got enough time. We can use analytic methods, so we can do these kind of relevant transformation methods to see what the model's basing its answers on, if you like. We can visualise audio features, or perhaps we can make some kind of interactive, perceptualised abstractions. I'm not going to steal Timo's thunder, actually. I'd bundle that data into CatArt, but it works really nicely, and I think Timo was going to share it as well, so I'm not going to steal his thunder. So he'll share that in a sec. That's sort of main frame, if you like, I wanted to introduce this session with. Thinking this through and being a mix of sort of machine listening workshops, and then also in musician and the more, as Chris would say, slightly hippie soundscape ecology workshops, or acoustic ecology workshops, let's say. So there's a really nice workshop in Hull of a very, very interdisciplinary acoustic ecology. So from the people with pure artistic research, slightly social concerns, and then ecologists. And ecologists would get up and say, well, we do soundscape ecology, we record 1 minute every 15 for 3 weeks, and then we analyse this results. And the field recorders would go, what do you mean you don't listen to your data? How on earth can you know anything? See data around. And it suddenly made me realise that they don't. You do know something by calculating these indices. You suddenly see by looking at these wide spatial extents and long temporal extents, you do start knowing something about the sound world in a way that you can't do through listening at one point in time. And it made me start thinking about these maybe different types of listening, of experiential listening, which is being in the world, listening in space for a long time, and what we might call empirical listening, which is something that maybe machine listening affords, maybe a new way of listening that machine listening affords. So I suppose a question for later on is like, how does, and it comes back really to Hans Holger, you saying in the very first session, are you machinising human listening? And just the way, and I slightly drunkenly said, I think Owen's become listening like a machine in some ways. And I think it does. I think it's starting to change the ways we as humans listen. We can't not, because we sort of reconceptualise ways of hearing. So that's maybe something to think about during this afternoon. That's enough, I think, by way of that introduction. Are there any questions while Demos sets up?
Just wondering if anyone's done any work resolidifying the audio analysis.
Well, that's exactly right. So I started trying to do it in web audio and I didn't get very far. Not that I know of, but that's sort of what I was getting at with this, is like, can we have the best of both worlds? So can we experience the sound, but in abstract ways so that we can take in loads of it? So definitely I think it'd be a really interesting thing to do. So there's been some, I forget his name, I used to have it, sorry, in some lecture notes. There's a guy who did some quite nice stuff, and he did use the classic archive of every number one since 1952 or whatever, and he made, it's basically like a modified phase vocoder, so that you got these just very slow changing spectral snapshots merged into one, like moving through databases. But even, what I was thinking of doing first up was you plug in a hard drive. There's the very simple problem of coming back from the field with a bunch of data. You plug in a hard drive and you get a grid of all the files, and then you literally just hover over. Even doing like a mean spectrum resynthesis, that kind of thing, I think would be really, really useful. But I certainly haven't come across anything like that so far. But that's exactly the sort of thing when I say perceptualise rather than visualise. I was thinking of whether we can resynthesize features.
Is the distinction between the kinds of listening there, is it similar to what goes on, it's kind of an art point out in the visual domain, like artists learn to stop seeing the world in a normal experiential way, but instead see it as having lines, and if you want to draw the railroad line going into the distance, you don't see it as parallel lines anymore, you see them as converging lines. You see, somehow the typical, one way of trying to draw the artist is to not see the normal, but see abstractly, and it's more concretely, I think it is. You don't add all that interpretation.
I think I was thinking of it a bit more like what satellite imaging has done in the visual domain, that we've suddenly massively zoomed out and seen the world from this much wider perspective. I was thinking about it more like that, in the sense that we can, but we don't have that we can't immediately hear in that zoomed out sense. So we have this kind of zoomed out perspective, but at the moment we can only experience that zoomed out perspective by looking at some outputs, some models.
Yeah, that's why I'm a bit confused. So I think a lot of the tools you're talking about, to me, they're only metaphorically listening, right? They're only listening that the data was originally sound data.
Yeah.
You're talking about visual displays,
as
opposed to, say, maybe other ways of actually retaining it in the audio domain, but listening to the entire Bible in 10 seconds or something. I mean, that would be the analog, that would be of retaining the audio domain, but just having it sped up or something. I know there are practical reasons why you don't want to do that. But that would be the analog of the satellite images zooming out. When you talk about being a machine listener, I would have thought or attending to the frequency response and the bands that are present.
Yeah, I guess there is that level of it as well. I think there's two. I mean, it was one thing. It came up in a bit in the first workshop when we were looking at oral history archive, and the historians were going, "Oh, she's got a really sexy voice," and I can't remember down on Parag or someone was just like, "Oh no, I was just listening for the sibilants or listening for the." So on that very simple level, if you're interested in clustering, you'll listen out for audio features that might afford clustering, and that's one way. But I suppose, this is very formative from. By empirical, I suppose I'm also getting at the fact that we can, thinking about this larger extent, this larger temporal and spatial, suddenly we can listen across time and space in a way that we couldn't before. But we can't just see it. So when we see a satellite image, we're seeing it in a zoomed out way, right? But we're still experiencing it in...
We've established visual conventions of scale to how does this image, which is really only a few inches across, how does it have a relationship to a visual scene that has many miles or thousands of miles across? We have conventions for establishing that, geometric convention, but we don't have this for audio. No. We don't listen to audio and say, oh right, this is a temporal compression of an event.
Some people, I suppose, might, if they've really done enough, I suppose if enough people have listened enough to Beethoven's Fifth and all those examples that Stockhausen gives, they might be okay with it. But you're right, and that's absolutely
something like the voice, that technology is an example of it. Trying to introduce a new convention, we use something, interpret it this way, and that's how we can put a lot of different, it isn't the normal audio relationship to the sound environment, but it's an arbitrary conventional that we've established. We could do something like that for audio information, not just time compression, it's only one possible.
Yeah, this is kind of related. I mean, I'm interested in this relationship between experiential listening and what you're calling empirical listening, because
I don't quite know what it means. Yeah, it's
Sorry?
Yeah.
Because one of them takes time. I mean, the notion of experience is a time-based one. The notion of listening is a time-based one. And what's just been said about the representational system that you're using is that it is an arbitrary visual convention for representing sound. I mean, it might have some kind of technical legs, if you like, but it is essentially a sort of convention for representing sound. And when you have a sonogram or a spectrogram of something which has the definition of the entire audio experience, it's possible to learn some kind of relationship between the listened experience and this arbitrary visualization technique. But you're suggesting that there's some value in that compressed empirical listening technique per se, and I would say that you only have any value in the second by virtue of having learned the experience of the first.
Yeah, and what I'm wanting, I suppose, is to have a cake and eat it.
Yeah.
And I would show, so what I would say, even with the way that Demos put CATARC together, you can explore a huge database, so you can have a kind of experience, possibly through the virtual interaction with a large data set.
Yeah.
So it's the beginnings of getting the best of both worlds.
Yeah, but that would be reliant on having had first a large amount of experience of learning what the relationship is between a full resolution spectrogram and the actual experience of the actual time experience of that sound. You have to learn to read the convention by relating it to the sound that you're listening to.
For a spectrogram.
Yeah.
Yeah. So I'm not suggesting the spectrogram is the answer. I'm just saying that's one way of doing it.
Yeah.
And I think there might be some interesting other. I don't know if we're talking quite close, but I totally agree with you.
Okay.
Completely agree with you. So these. Have you seen CATARC?
I guess what I'm interested in is the extent to which those kinds of conventions become become kind of invisible to the users, I
Yeah.
guess. So when composers first moved from working with tape to working with, representational systems in Pro Tools and things like that, they had some of their kind of suspicions about what a sound might look like confirmed, but of course you have to invert the logic there. That was confirmed because the people who made the software made the things look like what the people who were expecting sounds to look like would look like, if that's not convoluted, too convoluted to follow.
No, it's perfect.
And then within a very small generation of composers, people became able to manipulate sounds on the basis of the visual representation only in certain circumstances once they've learned that convention well enough. Yeah. And I guess I'm interested in the extent to which you could have a familiarity with sonograms and spectrograms, which I've been working with since the 1980s, really sort of when they were just really starting. And the extent to which that becomes something that's sufficiently intuitive that people could read a compressed form of it and make it meaningful. But yes, as you say, that's only one potential solution.
And I guess that's one of the key. It's just
I'm interested in
good
it.
design, isn't it?
I'm interested in it because I have a PhD student who's doing just this kind of project in the sense of the data gathering. He's done months and months of 24-hour recordings at 24 locations in one Amazon rainforest situation across a number of different weather situations, and he now has 24-track recordings of things going on for months, literally months. And his only way of approaching this at the moment is to actually listen to them all the time in multi-channel audio studios with loudspeakers around him.
Yeah.
It's taken a long time to do his PhD.
It is actually, yes. He's using it as an excuse for not submitting. I don't believe it.
That's exactly why we came to it. Patrice and I working on a project similarly with just like thousands of hours, and then you try and understand what your model's saying, and you need to listen to it, but you can't. So it's really practical.
The key point here that makes a difference is time.
Yeah.
And as soon as in that time, there's many repetitions and many things that sound the same. And when you can get rid of that repetition, then suddenly you can explore the space of expression of your object of interest much quicker. And just say, okay, there's this type of thing that happens, and that, and there's this something in between. But that number of clusters will be much less than the minutes and hours of actual time. That level of kind of fusing repetitive things, and then suddenly you can get a grasp of a long stretch of time.
I think it's Q cat art.